Hello, hello, hello. Am I audible? Okay. Hello, am I audible? Hello, am I audible? So I hope I'm audible. Welcome to discussion session 10 on diffusion, convection heat transfer and diffusion mass transfer. So considering the course part, we have covered the major portions. So far we have covered free convection part and diffusion mass transfer. We will be having the problem discussion session 4 and evaporation sublimation. In brief, we will be discussing. And after that, in one more session, we will be summarizing everything, the analogy part, how they can be done. So that part we can summarize, and we'll be having the doubt clearing session in the next session. Okay. So in today's content, we'll be discussing about evaporation sublimation. Then the one important aspect in heat chemical applications is the chemical diffusion mass transfer. Then we'll be having the problem discussions for where we'll be discussing a few important problems on this. Okay. So if you take evaporation as a case of mass transfer, so you can see here a lake is here. So usually when wind flows over the surface, there will be carriage of moisture along with it, right? Moisture added into this surface. So that will be continuously added into this surface. Also, there is heating. So due to heating, there will be vaporization. So that is continuously adding the moisture. So Q is one important part. The amount of moisture added is also another important part, right? So this can be visualized equivalent to an evaporation in a column. Maybe suppose there is a container like this, and there is a liquid A, and there is a binary gas mixture which consists of A and B. So what is A and B? Liquid is A and air is B. So we can assume that to be a dry air, suppose, not a wet, or it does not contain a moisture. So maximum it can take how much moisture it want to be. So this is the control volume in analysis. So any mass transfer, heat transfer would be happening within this control volume. So just above this water surface, there will be vapors of liquid, right? And you can see there will be the mole fractions of each constituents, XAO. XAO, what does that mean? Mole fraction of water vapor above liquid surface. And XBO, what is it? It is the mole fraction of air above the liquid surface. So see this. So we are traveling in X direction like this. So from here to here we are moving. So it is X equal to L. So that diagram is shown. So you see this. What about XA? What is happening there? So this is Xi at any interval. So you can see Xi is, as we move from here to here, this is equal to, here it is 1, Xi. So this is XB is maximum, which is at the top. As we move to the inward, Xi will be maximum, right? Okay, so the total concentration can be expressed as a sum of Ca plus Cb. Okay. So that can be expressed as a sum of Ca plus Cb. Also, the sum of mole fractions at any section would be 1. Xa plus Xb would be 1. And the mass flux, this is NaX double prime, which is CdAbL into Ln into 1 minus XAL by XAO. So we already know NaX is CdAb by L into, right? CdAb into delta X, right? Or delta C. That will be that general expression. dAb by L into delta C. So concentration difference, that will be the mass. But see the difference here. Why is it happening? Because the air is flowing. So there will be a relative flux between the air and water species. So in the equilibrium condition, that fluxes should match. So the net NaX can be determined from that. So you can just refer minus del A plus that convective part will be there. So simplifying that and solving, we will be getting this expression. So the derivation is available, especially it's available in Cropera and any convective or diffusion mass transfer textbook. So very simple derivation. So this is the final expression for that. Okay, right. So let us have a quick look at sublimation based. It's a kind of mass transfer. So sublimation, it's the direct phase change from solid to gas, or maybe gas to solid, etc. So there is no solid, liquid, gas. It's a direct transformation from this, or a direct transformation like this. So this intermediate part is gone. Any intermediate phases are gone. So that is a kind of mass transfer. For such analysis, we can do the Raoult's law analysis, which states that P at the surface, which will be equal to ratio of the pressures, and that will be equal to the mole fraction. So from that, concentration of a particular substance can be related to its solubility. As I mentioned, the C by P, solubility of a gas or substance. How much it can be dissolved in a substance. So that is dependent upon the concentration as well as this pressure also. So both factors are very important in determining the. Okay. Then another case is mass diffusion with homogeneous chemical reactions. Okay. So just as heat diffusion may be influenced by internal source of energy, species transfer by mass diffusion can be influenced by homogeneous chemical reaction. So what is a chemical reaction essentially? Suppose a species A reacts with B, giving C. Okay, so a new mass is created. If like suppose in a mixture of containing of A and B, we all in all our previous assumptions we can see, we assume that they are non-reacting. Why? If they react, A can be react to give a third species C. So then no more that diffusion coefficient DAB is valid, right? Then that diffusion coefficient is not valid. So for that, we need to have DAB, then it should have in DABC to be perfect. But it's not defined, so it's DAB itself. So when species react, then we can see here the governing equations itself changes. And the analysis is slightly different, which is actually not discussed in this part, right? So even in the particular species, if they are not reacting, suppose A and B are also not reacting and they are giving a third species, they can be analyzed. So you can refer more that how that analysis is done, which is actually currently not a part of our discussion right now. So what we can do is This is the governing equation for that. dAB into d square, in a perfect diffusion equation, it is d square Ca by dx square equal to 0. But here another term gets added. This is the generated mass rate, because it is actually created from the chemical reaction. It is equivalent to our heat with internal heat generation. In internal heat generation, we know, suppose if it in a particular substance, if mass is entering and leaving like this, and a heat is actually liberated or it enters, right? So this is equivalent to that heat generation part. Okay. So for a zero order reaction, that it is Na is equal to K0, and a first order reaction, that value is going to be Na equal to K1 into Ca. This is actually proportional to the concentration. So there are first order reaction, second order reaction, third order reaction. They are all part of a chemical kinetics. So chemical part also comes into picture. So this is very essential when we are studying something related to combustion and all. So there, this kind of substances will be created. So then this analysis would come into application. So there you shouldn't treat it as a without mass generation or mass diffusion. So chemical reaction is already included. And some special cases of diffusion mass transfer, as I mentioned, this is diffusion mass transfer with chemical reaction. Then there can be catalytic surface reaction. Catalytic. So this is catalyst based. So what is catalyst? It controls the rate of a chemical reaction without actually taking part in the chemical reaction. Okay, so if A changes to B in presence of C, suppose this is an equilibrium reaction. So a third substance C will actually control this rate. Okay, so that is actually helping the reaction to occur faster or lesser. It can control both. So it can either reduce the rate of reaction or increase the rate of reaction. So when that happens, the order of this reaction, so the mass generation may be affected. The mass generation rate, so that will be affected. The rate of mass generation, the ability to which that system accelerate to attain equilibrium system, right? Okay. So let us go to, today we'll be having some 3 important problems which can be part of our problem discussion session 4, which is our final problem discussion session. So in that, related to diffusion mass transfer. Okay. So the question is, it's a very simple question, like it's good understanding, would give you much more understanding of the topic. So the question is, there is an open pan of diameter 0.2 meter. So this dia is 0.2 meters. Okay. And at height 80 mm, there is water. 80 mm is how much? 0.8 mm, 0.8 meter, right? Or 0.08. Okay, 0.08. Okay. So that much water. And is exposed to ambient air at 27 degrees Celsius. And the ambient air is 25% RH. Question is, determine the evaporation rate, assuming that only mass diffusion occurs. Okay, so no convection, mass transfer, etc. occurs. Determine the evaporation rate considering bulk motion. So first question is, if diffusion alone occurs, what is evaporation rate? If bulk motion occurs, what is the evaporation rate? So their comparison, how will they vary? Okay. So we assume, first of all, assumptions. Steady state conditions, one D diffusion, constant properties, uniform temperature and pressure, and perfect gas behavior. Okay. So water vapor air at 300 Kelvin and 1 atmosphere, and saturation pressure is equal to 0.03531 bars. Okay. And specific volume is equal to 39.13 meter cube per kilogram. So from steam tables, you determine these properties. Okay. So if you look at a schematic diagram like this, there is a water at 27 degrees Celsius, and ambient relative humidity is 25%. Pressure is 1 atmosphere. So from that we determine that. Okay. And specific volume we have determined. So so water vapor air mixture. So temperature is mentioned, and first question is evaporation rate considering only diffusion. So then NAX equal to minus DAB into A into DCA by DX. Okay, we know the basic equation. So area is this area of the pan, and the mass flux is this NAX. Okay. So if we have seen the previous evaporation case, so we are not considering in that manner that equation. First, you will analyze if it is like this. So only mass, no bulk motion. Bulk motion is not there. Okay, so we cancel that. So let us see how that will be estimated. So DAB value and phi equal to P saturation. Is it correct? No, PA by P saturation is given as 25%, the ambient. Okay. And that is equal to Ca by Ca saturation. So A means this is that which component? Yes, the outside air. So B is our liquid. Okay. So this expression can be also written as minus DAB into A into Ca infinity minus Ca surface. So there is a concentration here at surface. There is a concentration here in the ambient. So due to which from higher concentration to lower concentration, the diffusion of the vapor happens, the water happens. So it will be in this direction. Okay. So the bulk motion means that what does it happen? Here we are not considering the bulk motion. How does that bulk motion is actually created? So there is vapor transferred from here to here, right? Similarly, there can be the species air transferred from here to here. because here that concentration is lesser, isn't it? So let me write that again. So there is species A, which is actually getting evaporated into the outside. So because here Ca, this is surface, and Ca infinity. So CAS is greater than Ca infinity, right? So that's why it is happening in this from higher concentration to lower concentration. Evaporation is happening. So if it is species B, which is maybe the air, then Cb infinity is there, Cbs is there. So Cb infinity is very much higher than Cbs, right? So there will be in this direction, there will be another flux. So both of them together will exist, right? So they are called as the bulk motion. So there will be a net flux actually at any cross section if you take. At any cross section if you take, there will be in this direction of species A and in this direction the species B. And they are relative to each other, so that we can combine them and write the equation. Okay. So currently in this first part, we are not considering the bulk motion. No bulk motion. That is not happening. So can we assume like that? Yes, in some cases when the concentration difference is very small, we can assume like that. So we'll assume it like that and see. So if we rewrite the equation, NaX equal to minus DAB into A into Ca infinity minus CAS by L. Okay. Which can be also represented as minus DAB into A by L into 1 minus phi infinity into CAS. Okay. So we can substitute the values 0.26 into 10 raised to minus 4 into pi by 4 into 0.2 square by 80 into 10 raised to minus 3 into 1 minus 0.25. Okay. So finally we will get that value to be 1.087 into 10 raised to minus 4 kilomole per second. Okay. And CAS is equal to 1 by Eg into mu A. So mu A is actually our molar mass. For water it is kilogram per kilomole. So just we will substitute that, and just from that we can get the corresponding values. Okay, concentration we can determine. So this is the evaporation rate. So this is not in terms of heat, it is in terms of mass. So mass flux into, if you have that heat carried by that specific heat, it's in the vapor state, multiply, you will get the total heat carried away by this evaporation. Just you need to substitute it by HFG of the vapor. Okay, now let us consider bulk motion. So bulk motion. Bulk motion is considered. Then we will use the previous expression, NaX equal to CDAB into A by L into ln 1 minus XAL by 1 minus XAO. Okay. So C equal to T by RT, okay, is equal to 1.0133 by 8.314 into 10 raised to minus 2 into 300. So if you substitute that, you will get the value to be 0.04063 kilomole per meter cube. P equal to 1 atmosphere. The mole fraction at x equal to 0 and x equal to L are XaO equal to PAS by P, which is equal to 0.03531 by 1.013. So that will be 0.0348. And XaL equal to XaO into pi infinity, which is equal to 0.0087. Hence, we can write NaX equal to 0.04063 into 0.26 into 10 raised to minus 4 into pi by 4 into 0.2 square by 80 into 10 raised to minus 3 into ln 1 minus XAL 0.0087 by 1 minus 0.0348. And that value comes to be 1.107 into 10 raised to minus 8 kilomole per second. See, so let us, so no bulk motion. Bulk motion, as I said, all the species in movement. Okay, then that value, what is that value? 1.087 into 10 raised to minus 8. Then bulk motion 1.107 into 10 raised to minus 8 kilomole per second. Okay, so you can see the difference. So this is more kind of considering the bulk motion, so that is more closer to the reality. Okay, so the bulk motion actually tends to increase the evaporation rate. So when the ambient conditions are more, that factors will obviously be increased, right? So that factor also comes into picture, right? So considering the next question, a laboratory apparatus to measure the diffusion coefficient of vapor gas mixture. So it determines the vapor gas mixture, maybe DAB factor, consists of a vertical small diameter column containing the liquid phase. So this is a liquid phase that evaporates into the gas flowing over. Okay, the gas flow rate is sufficient to maintain a negligible vapor concentration at the exit plane. So the gas flow rate is sufficient to maintain a negligible vapor concentration at the exit plane. The column is 150 mm high. And the pressure and temperature in the chamber are maintained at 0.25 atmosphere and 320 Kelvin. So these are the inside conditions. Okay. For calibration purpose, you have been asked to calculate the expected evaporation rate. Kilogram per hour meter square for a test with water and air undergoing under the foregoing conditions. Using the known value of diameter for DAB for vapor air mixture. Okay, so you need to calculate the expected evaporation rate for a test with water and under 4, so using a known value. So let us see how that problem can be solved. So first of all, let us assume steady state conditions, 1D diffusion process, constant properties, uniform temperature and pressure throughout the column. So temperature and pressure constant. Water vapor exits ideal gas behavior. So water vapor exhibits ideal gas behavior. Okay. Negligible water vapor in the chamber air. So we know actually the coefficient is DAB is P inverse into T raised to 3 by 2. Okay. So T raised to 3 by 2. So from if you are able to determine the P and T conditions, we can successfully determine that concentrations, right? So DAB value can be 0.26 into 10 raised to minus 4 meters square per second into 1 by 0.25 into 320 by 298 raised to 3 by 2. Okay. Because that ratio is like this. So from the standard condition, we can determine the ratio of D by DAB. Okay. So we are getting that value to be 1.157 into 10 raised to minus 4 meters square per second. So next our analysis is similar. This is just an evaporation process. We will consider the bulk motion. Bulk motion condition. Okay. So we know that evaporation rate or mass flow rate is, as I mentioned earlier, it is NAx equal to CDAB by L into Ln 1 minus XAL by 1 minus XAO. Okay. So C become equal to P by RT, and that value comes to be 0.25 by 8.205 into 10 raised to minus 2 into 320 into Ln 1 minus XAL by 1 minus XAO. So we need to determine that values. So XAL is 0 because at the top of the column, no water vapor. Vapor is 0, dry air. So here at XAL. So that will be equal to 0.153, 1053 by 0.25, 0.4212. So where PA is the saturation pressure for water at T equal to 320 Kelvin. So substituting the values, NaX equal to 0.009397 into 1.157 into 10 raised to minus 4 by 0.15 into ln 1 minus 0 by 1 minus 0.4212. 3.964 into 10 raised to minus 6 kilomole per meter square second. Okay. Or on a mass basis, NAS into mu A. So that value comes to be 3.964 into 10 raised to minus 6 into 3600. So into 18 molar mass. So which is 18. So that value comes to be 0.257 kilogram per meter square ounce. So that is evaporation rate. Okay. So it's a column that is diffusing into the air, flowing over the mouth of the column. So evaporation rate of the water using the known value of binary diffusion vapor we have determined. So we have assumed a steady state condition, determine the diffusion coefficient using the standard values of that, and we got at 320 Kelvin and the temperature changes, we have determined the diffusion coefficient. From that we have determined the vapor concentration at the XAO and XAL. So it's actually following a curved path. So that is the concentration variation and we are getting the values. Fine. The problem is solved. Next to the problem. Question is, there's a spherical droplet of liquid A and radius R0 and it evaporates into a stagnant layer B. And we have an expression for the evaporation rate of species A in terms of the saturation pressure species of A, P of R0 and P of saturation. The partial pressure of species A at an arbitrary radius R and pressure of R and the total pressure P and other pertinent quantities. Assume the droplet and mixture are at uniform pressure P at P and temperature T. Okay, so evaporation spherical droplet is given and the radius of RO. So it is having a radius RO and evaporating into a stagnant gas B. So evaporation rate of species A in terms of then partial pressure PA of R, total pressure P, and other pertinent parameters. So we assume steady state condition. One day radial diffusion species. Constant properties including total concentration. Then we assume droplet and are at temperature and pressure, and there are perfect gas behavior. So evaporation of liquid A into binary gas A plus B is, so it's actually a liquid which is diffusing into an air, right? So this is a process happening. Between them there is an interface. So that interface is actually changing in size. Okay. So we will write the equation. So NAR, so it's in the spherical coordinate actually. So this is in the radius R. So NAR is equal to minus DAB into AR into DCA by DCR. Okay. Plus CA by C into NAR. So this is actually the what species? Our bulk transport part. Actually, that's the species which is actually in balance with species A. So AR equal to 4 pi r square. So if it is expanding or something, radius is changing, area is 5 pi or 4 pi r square. So Na into 1 minus Ca by C is equal to minus DAB into 4 pi r square into DCA by dr. Okay, so Na into, we are just rearranging the terms. So this term and this term we can rearrange, and we will be getting Na into 1 minus Ca by C equal to minus DAB into 4 pi r square into DCA by dr. Okay. So we can write it as Na into P minus Pa is equal to minus DAB into 4 pi r square into. So DCA by dr, we know Ca equal to P by RT, right? Ca equal to P by RT, Pa by RT. And C equal to P total by RT. So just writing that. So it is P by RT into dPA by dr. Just substituting this term inside, and other factors are constant. So 1 by RT would come outside and dPA by dr would be there. Okay. So just we are rearranging. I am once again write the equation. So Na into P minus Pa is equal to minus DAB into 4 pi r square into P by RT into dPA by dr. So just bring this term to the other side. So other factors are constant. So minus Na into RT by DAB into 4 pi is equal to integral dr by r square, we can write, which is equal to dPA by P minus P integral. So just integrating that because all are in differential form. So it is from 0 to R. This from P at R0 to P at R. So P at R0 to P at R, which consists of A plus B mixture. Here only A mixture is. So this is actually diffusion to the species by the expansion. So just integrate that. We will be getting N equal to 4 pi R0 DAB into P by RT. Okay. Into 1 divided by 1 minus RO by R into P minus PA of R by P minus PA of at the initial original place. So if we need a particular radius at a particular point, we know we can see the diffusion of the species into the mixture. Okay, so PA of R0, what is that? It is equal to PAO, which is a saturation pressure of liquid at temperature T, right? So that's the case. So finally we get that expression, right? Okay, so if you substitute that, you will get the corresponding values. Okay. So that's all for the discussion session today. So in the next session, we'll be discussing the analogy between heat and mass transfer. We'll take a summary and quick summary, and if there are any doubts, we can clear that and we can wind up the session. Thank you. I hope that there are no doubts. If there are any doubts, you can always mail me. Okay. Okay. So thanks for joining. We'll see you next Sunday, next week, so that we can possibly discuss and that wind up the sessions. Thanks for joining. Thank you.